Hi everyone, welcome back to MATA35. This is the start of week 10, so there are only 3 more weeks of lecture left, and we're going to be talking about systems of linear ODEs. One of the nice things is that we can apply many of the techniques that we learned in Wednesday's class to solving these things once we take a system of linear ODEs and translate it into a higher order ODE. And of course, this means that we'll also get the chance to practice many of the techniques that we did learn and went through a little bit fast on Wednesday. So let's get started. Let's start with a system of 2 first-order linear ODEs. So one thing that you should watch out for is in the past, we've normally used x as the independent variable and y as the dependent variable. Here, for all the examples in the systems of ODEs, we're going to let t be the independent time variable, and we're going to let x and y be 2 different dependent variables. This is going to be useful when we start graphing out autonomous equations, because then the x and y axes make sense. So just watch out for that. So now, instead of dy dx, we're going to be doing dx dt and dy dt. And so we're going to first talk about a homogeneous system of 2 first-order linear ODEs, which is going to be, we're going to have 4 constants, a, b, c, and d. And then we're going to have, say, dx dt is equal to ax plus by, and dy dt is equal to cx plus dy. Another way that you'll see me write this often is you'll see me write this as x dot is equal to dx dt, and y dot is equal to dy dt. This is one of the reasons I gave you that notation earlier on, is because this is a notation that we'll be using throughout this week and next week of lecture. So that is a homogeneous system of first-order linear ODEs. So you note that one of the differences is that these are linear, but they're linear in both variables. So you both have a copy of x and a copy of y times some constant. And we're going to also talk a little bit about an inhomogeneous system of 2 first-order linear ODEs, where you have some f of t or g of t. X dot just means x prime. Yes, so I'm using x dot to mean derivative with respect to t. Whereas I've been trying to use prime to mean derivative with respect to x, but yes, it just means the derivative of x. And this is just a slight notational change, which if you continue on and do any sort of modeling, this is a very common notational usage. Okay, so this is the basic problem setup. So instead of just having one equation, we have 2 related equations now. They're both first order, so they're not too bad. But we have 2 equations, and we have to solve them simultaneously. So now, if you think back to how we solved systems of 2 equations when they're ordinary equations, one method of doing that is you set y equal to something, and then you substitute that in, and that's going to be basically what we're going to be doing today. This is going to be the reduction method for solving a system of 2 first-order linear ODEs. And what we're going to do is we're going to first convert a system of 2 first-order linear ODEs by converting into a single second-order linear ODE. So let me walk through this as we go on, and feel free to stop me with any questions. So let's walk through this with the example, let's say x dot, so let's dx dt is equal to, let's say, x plus 2y. And let's say we also have y dot, which is equal to dy dt, is equal to 4x minus y. So this is a homogeneous system of 2 first-order linear ODEs with constant coefficients. The next thing we're going to do is we're going to compute x double dot, so the second derivative with respect to x, as a function of x, y, and y dot from the first equation. So if you take the first equation and you take another derivative with respect to t, you're going to get x double dot is equal to x dot plus 2y dot. Homogeneous means that you don't have... So that's a little bit complicated, but basically the way to think about it is homogeneous means that when you have the x dot is equal to something, it is linear in x and linear in y. So you have some constant in front of x and some constant in front of y and nothing else. So that's what homogeneous means here. So we don't have any sort of f of t here. We don't have anything there. We don't have a plus 5. We don't have a plus t. We have none of that. That's what homogeneous means here. And what you'll see is that when we convert this into a second-order linear ODE, it means homogeneous in the regular way. Okay, so the first thing we did is we took this equation here and we took the derivative, so we applied d dt to the entire thing. So when you apply d dt to x dot, which is dx dt, you get d squared x dt squared. And so that's equal to x double dot. Okay? And you do the same thing for x plus 2y, and you get x dot plus 2x 2y dot. So you've added a dot to everything by taking the derivative with respect to t again. Okay, so that's the first step. So we convert this into, we take the derivative and we get a second order linear ODE. But now this isn't so helpful, right? Because we don't know what, we still have this y component. So the next thing we have to do is, well, let's get rid of the y dot. Why am I writing? Come on. Yes. So the next thing we're going to do is we're going to eliminate y dot by substituting into the second equation. So here, notice that we have y dot is equal to 4x minus y. So that means that x double dot is equal to x dot plus 2 times 4x minus y. Or x double dot is equal to x dot plus 8x minus 2y. But now we still have a y here, right? So we need to get rid of that as well. So let's eliminate y by substituting in the first equation. And so notice up here, you can convert this into the equation y is equal to x dot minus x divided by 2. Okay, so we subtracted x from both sides of that equation and divided by 2. And so we know what y is in terms of x dot and x. And so we can substitute that in as well. So when we do that, this gives us x double dot is equal to x dot plus 8x minus 2 times x dot minus x divided by 2. Now you notice that this example was carefully constructed in the book so that some of the coefficients cancel out. So this is actually one of the examples in the book if you're following along. And when we simplify this a little bit, what we get is x double dot is equal to x dot plus 8x minus x dot plus x. Oh, sorry. And of course, these two pieces cancel out. And so you're left with x double dot minus 9x is equal to 0. Could we just substitute x dot because it will be plus 2y and minus 2y? Let's see, where did we mean that? So what we're trying to do is we're trying to eliminate one of the variables. And you can do this by either getting rid of the x variable or getting rid of the y variable. But it turns out that when you have this when you have the system of two linear first order ODEs, in order to get rid of the substitute in y dot, well, you need to take another derivative of x dot. Did that answer your question? Oh, sorry, I skipped a step. I need to be more careful about skipping steps. So this implies that x double dot is equal to 9x. And we subtract 9x from both sides, and you get x double dot is minus 9x is equal to 0. So all we're doing here is we're trying to do some algebraic manipulations to get rid of one of our variables. Because once we've gotten rid of one of our variables, then we're back in the single variable case, and we know how to solve those things. Okay, let's continue, and so now the next step is, now we're going to solve the second order ODE. And notice that when we've rewritten it this way, this is actually a homogeneous linear ODE with constant coefficients. That's why we called the other one homogeneous. The other version of it homogeneous. So now we have this, we can solve for x. And there are multiple steps to this, of course. Let's walk through them slowly. We covered them on Wednesday, or Wednesday and last Friday, but let's walk through them all carefully again. So the first thing we're going to do is we're going to find the eigenvalues, or the roots of the characteristic equation. So that is, our equation is x double dot minus 9x is equal to 0. And so that means when we go to our characteristic equation, we have lambda squared minus 9 is equal to 0. So lambda is equal to plus or minus 3. Okay, so that's our first step. And then the next step is, well, we solve for x. Well, this is pretty easy once we have since this is a homogeneous equation with constant coefficients. So when we solve for x, all we have is x is equal to some constant times e to the 3t plus some other constant times e to the minus 3t. We're going to call this constant C1 and C2. Okay, so we now have solved for x. But of course, in our original equation, we had both x and y. So we also need to solve for y here. So when we're solving for y, well, remember we had from the previous slide, we had y is equal to x dot minus x over 2. So y is equal to x dot minus x over 2. And we can plug that in, right? So we need to compute x dot. So x dot here, we can rewrite it in terms of why are there the c's? Oh, because remember, this was the process for solving a homogeneous linear equation with constant coefficients. You have the two solutions. You have the two solutions, e to the 3t and e to the minus 3t, and then you add constants to them to get the general solution. But now when we take x dot here, we end up with 3 c1 e to the 3t minus 3 c2 e to the minus 3t. Because you've just taken a derivative with respect to t. Okay, so now we've done that, well, now we know what y is because we can just plug in for y. So y is equal to 1/2 times, well, x dot, which is 3c1 e to the 3t minus 3c2 e to the minus 3t. So that's x dot minus x. So what's x? Well, minus c1 e to the 3t plus c2 e to the minus 3t. Okay, so all we did is we substituted in x dot and x into our equation for y. And when we simplify that a bit, that ends up being y is equal to minus c1 e to the 3t plus 2c2 e to the minus 3t. And of course, we originally had x is equal to c1 e to the 3t plus c2 e to the minus 3t. So note that we now have a solution for both x and y. This is the general solution for both x and y, and so if we had initial conditions, then we could solve for both of them simultaneously. Note that the c1, you have to be a little bit more careful with your constants when you're working with multiple equations, because you can't just combine together constants anymore. So once you've, don't we need the 1/2? Oh, I already did the 1/2 implicitly, so sorry, I skipped a step here, which is, if you'll notice, this 3c1, and this is minus c1, so that gives you 2c1 e to the 3t. Divide that by 2, and you get, oh, did I get a, I think I may have gotten my signs wrong. What did I do here? c1 e to the, sorry to, I think I might have gotten my signs wrong. So let's go ahead and double check what we did here. So we had 3c1, did I do that right? X dot minus x. Okay, well let's, I assume I did something wrong here, and hopefully I didn't mess up all my notes. But so let's actually walk through that. So that's 1/2, that's 3c1 minus c1. And we had minus 3c1. That is a little bit odd. X dot minus x. Minus x. Okay, I think that I must have made a mistake here, but let's keep on going and see if these things will work out magically. So if we had this, that should be 3 minus 1, so that's 2, so let's divide by 2, yep, so that's minus 3 minus, okay, I think I just had the negative sign messed up. So I think this should end up being a minus 2c2, because you had a minus 3 here, and you had a minus 1 here. So that would be minus 4, so it's minus 2c2. Does that make sense? I think I might have confused you with a negative sign there. Okay, so now let's keep on going. So unfortunately my notes are now all messed up, but that's fine. We'll solve this on the fly. So now if there are initial values, we need to plug them all in. So for example, let's say we've solved for this, so x is equal to c1 e to the 3t plus c2 e to the minus 3t, and y is equal to c1 e to the 3t minus 2c2 e to the minus 3t. Is that what I had? Yes. Okay, so now what we have is if we had an initial value problem, if we had an initial value problem, x of 0 is equal to, let's say, 2, and y of 0 is equal to minus 1, well, now we need to solve for those, right? So we plug those in. So if you plug in 0, then x of 0 is equal to 2. So 2 is equal to c1 e to the 0t plus c2 e to the minus, well, also to the 0, minus 3 times 0. So this is e to the 0. Both of these are e to the 0 here. And here we have minus 1 is equal to c1 e to the 0 minus 2c2. Minus 2c2 e to the 0. But of course, e to the 0 is just 1. So 2 is equal to c1 plus c2, and minus 1 is equal to c1 minus 2c2. And when we solve this, if we add these together, you'll, if you subtract one from the other, you'll end up with, let's see, what is that? This minus that. 3 is equal to 3c2, so c2 is equal to 1, and we also get that c1 is equal to 1. So you can check that those actually make sense. And so therefore, our final answer, given this set of initial conditions, is x is equal to 3 to the et plus e to the minus 3et, and y is equal to, let's see, so that's minus c1, so that's minus e to the 3t minus 2 e to the minus 3t. What exactly are we trying to solve for again? So originally we started with this example here. So x dot, we started with this example here, and we want to find some x and y that satisfy that set of differential equations. And so the first thing we did is we solved, the first thing we did was we converted it into a single second order linear ODE. And we solved that second order linear ODE and then substitute back in to get both x and y. So this is the general solution. General solution. And here in the second, in this next slide, I was talking about if there are initial values, which are these here. So I've just created these initial values, and I'm asking if these are the initial values, what are our equations x and y? And so what we did is we plugged those initial values in, and then we solved for x and y down here. So this is a specific solution given these initial conditions. Okay, so let's walk through. So the general solution has constants c1 and c2. Yes, exactly. So the general solution here has constants c1 and c2. Because whenever you have a general solution, you have multiple c1s and c2s and c3s, right? So that's one of the things we've been doing for the last couple lectures. Now, in general, you don't know what those c1s and c2s are. In fact, you can put any real number in there, and it'll still satisfy your equation. Sometimes you want to pick a very specific example of such an equation, and in that case, that's only possible if you give initial conditions. So if you start at a particular place, so if you say at time 0, x is equal to 2, and at time 0, y is equal to minus 1, well then that gives you a specific solution. Okay, so let's have you all try it out, and I will walk through this step by step. So instead of just asking you guys to solve the entire thing like I did last time, which was probably a bit too much, I'm going to walk you through this step by step. So the first thing is we have an equation. We have an equation x dot is equal to y dot is equal to minus x plus 2y, and we have two initial conditions. Okay, so now the first thing we're going to do is we're going to find x double dot, so the second derivative of x. So these are your options. What is the second derivative of x? Okay, so what we're basically doing here is we want to apply, we have x dot is equal to y, and we want to apply y, and we want to apply d dt to both of these. Okay, and when we do that, what you end up with is you end up with x double dot is equal to y dot. And so that is indeed d right here. Okay, hopefully that made sense. And so that's the first step, is you find x double dot. You could, in theory, do it instead and set y, find y double dot and get rid of all the x's. But for this example, we're going to get rid of all the y's from an x equation. But now we haven't gotten rid of all the y's because we still have this y dot here. So now step 2 is let's get rid of the y dot. So when you're trying to get rid of y dot, which of these is it? Is that a y prime or is that a comma? Oh, there. That's a comma. Go away. There. Hidden. You can't see it anymore. Yep, thanks for the clarification. Oh, I need to reset. Okay. So now the second thing is we're going to get rid of the y dot. So which of these is it equal to now? So what we had is we had x double dot is equal to y dot. But we already know what y dot is. So that's equal to minus x plus 2y. And so that is B right here, which it does look like people have been replying. Okay, so all these steps make sense, right? So we've gotten rid of y dot, but then the next thing we have to do is we have to get rid of y as well. And let's rewrite it. So which of these is it? Okay, let me reset the chat again. Okay, and so what we're going to do is we're going to get rid of y and rewrite. And so the first thing we notice is that here I chose a very easy example because we have y is just equal to x dot. So if y is just equal to x dot, then what we're left with is x double dot is equal to minus x plus 2x dot. And we can rewrite this as x double dot minus 2x dot plus x is equal to 0, which is again b. Okay, so all we've done here is normally whenever you're trying to solve a system of equations, well, you have to substitute to get rid of one of the variables, right? In this particular case, it's a little bit harder because you have to get rid of the variable's derivative first and then get rid of the variable. But then at the end, we've gotten rid of the variable, gotten rid of y and all its derivatives, and we're just left with x double dot minus 2x dot plus x is equal to 0. Why can't we use the second equation to get y is equal to something? You can. So you can also use the second equation directly. But one of the things that will happen is when you're solving for ordinary equations, if you use the wrong combination of equations, sometimes you just get like 1 is equal to 1. So it's not useful anymore. You could have done this the opposite way as well. So you could have found y double dot is equal to something and gotten rid of all the x's. So that also works. Okay, but now we got rid of all the y's in this particular case, and so now we're left with an equation that just has x's. What do we do? Oh, wait a moment. I should have... What just happened? Seems that I forgot to erase all this. Okay. Well, that unfortunately means that this solution is going to be a little bit obvious. Let me see if I can do something about it. Okay. So you always need to use the first equation to solve for y to get that. Not necessarily. So what you need to do is you need to... Okay. So you always need to use the first equation to solve for y to get that. What does that mean? No, you could also always use the second equation instead, and that would still get you something quite similar. Let me pause the recording for a moment, and I need... Okay, we're back now. Sorry about the technical difficulties. So now the next step is we're going to try to... Yep. So next step is we're going to try to solve for this ODE. So we started with x double dot minus 2x dot plus x is equal to 0. And we need to solve for this ODE, and the question is which of these is the general solution to this homogeneous ODE? And let me reset the chat. Okay, it looks like people think it's C. Well, The process for this is, of course, we start out by finding the characteristic polynomial, and setting that equal to 0. And that lets us find the eigenvalues. This is lambda minus 1 squared is equal to 0. So lambda is equal to 1 with multiplicity 2. Which then implies that x is equal to c1 e to the t plus c2 t e to the t. And this is another one of the places where you have to be really careful. I know that in the previous examples, I said that you just need to add an x to it in order to get another independent solution. But since here t is our independent variable, and so you actually need to add a t to it rather than an x. And so the answer is actually D here. But that was really tricky because in the previous examples we said, oh, you just have to add another x to it. But that was because we were taking things to e to the x, e to the lambda x. So in this case, because we have e to the lambda t, since t is our independent variable, the answer here is actually x is equal to c1 e to the t plus c2 t e to the t. Does that make sense? So this is one of those things where you have to be a little careful about what variable is your independent variable and what variable is your dependent variable. Okay, so hopefully that made sense. And the next thing we do is we just need to plug back in to solve for y. So remember, y is equal to x dot. So what is y equal to? Oh, can you explain that again? Yes, yeah, while you guys are working on it, let me explain that again. So basically, normally when we have lambda is equal to 1, you have e to the x as a solution, right? But if you have multiplicity 2, you add an x to it. And so you have x e to the x is a solution. Or x squared e to the x is a solution if you have multiplicity 3, right? So now the problem here is we have e to the t. And so because it's e to the t instead of e to the x, you need to add a t to it instead of an x. Does that clarify things a little bit? Because t here is our time variable, not x. Okay, and it looks like people have been replying to this one here. So y is equal to x dot, and so then y is equal to c1 e to the t plus, and you have to make sure to use the yeah, so here what we have is both this and e to the t are solutions, and so then you take c1 plus that plus c2 times this. Okay, so we have a number of different guesses for this last part. Well, what we have to do? We have to take derivatives. But now you have to remember that when you take derivatives with respect to t, you need to remember the product rule. And so when you take the derivatives here, well, the derivative of e to the t is just, of course, e to the t. So that's fine. But then you have d dt with respect to c2 t e to the t. And so when you use the product rule, you get y is equal to c1 e to the t plus, well, you have c2t times the derivative of e to the t, which is just e to the t. So we have c2t e to the t. But you also have e to the t times the derivative of c2t, which is just c2. So plus c2 e to the t. Okay? And this is because we're applying the product rule. So let me write that down. Product rule. Because when you take the derivative of a product of two functions, you need to take the derivative of one times the derivative of the one part times the derivative of the other, and the other times the derivative of the first part. How do we know what y is equal to? Oh, because that was given to us originally. So remember, we had y is equal to x dot. So this is all the same problem. So we're still working on the same problem here. Okay, so y is equal to x dot. And now we need to keep on going. And so we had the product rule, and now we can combine things together. So y is equal to c1 plus c2 e to the t plus c2 t e to the t. And so that gives you b here. Okay. And so this is a little bit tricky because one of the things you have to watch out for now is every time you see x is no longer our independent variable. And unfortunately, this is just the notational convention that different textbooks will use, as well as the different types of problems we use different conventions. And so often when you dealing with single variable calculus, the convention is that y is your dependent variable and x is your independent variable. Unfortunately, when you're dealing with this sort of multivariable calculus and ordinary differential equations with multiple variables, usually the convention is that t is your independent variable and x and y are your dependent variables. And unfortunately, this is just mathematician convention, and mathematicians are often will use variables in different ways, and so you have to watch out for that. Okay, so now we've solved for x and for y, but what else do we need to do? Well, we still have the initial values, right? So we still need to plug back in the initial values. X of 0 is equal to 1, and y of 0 is equal to 3. And note that, of course, here, this is saying t is equal to 0 and t is equal to 3. So what were our equations? Our equations were x is equal to c1 e to the t plus c2 t e to the t, and y is equal to c1 plus c2 e to the t plus c2 t e to the t. So now we need to plug that in and find the final equations. So what are c1 and c2? Let me reset before you reply to this. So now you need to plug in and solve for c1 and c2 based on saying when x is when t is equal to 0, x is equal to 1. And when t is equal to 0, y is equal to 3. Okay, looks like we have a couple of responses. Okay, so let's solve this together. So we had 1 is equal to x of 0 is equal to c1 e to the 0 plus c2 times 0 e to the 0, which is just equal to c1, of course. And so c1 is equal to 1. And in the other case, you had 3 is equal to y of 0, which is equal to c1 plus c2. And so that implies that c2 is equal to 2. And so yes, the answer is indeed B here. And that gives us our final answer, which is that x is equal to e to the t plus 2t e to the t, and y is equal to 3 e to the t plus 2t e to the t. So that's our final answer to this initial value problem. Okay, and that took a while, but hopefully that made sense. So basically, you have to go through all the steps. The first step is you convert it into a higher order linear ODE, which we know how to solve. And then we solve that, and then we plug those things back in to get both x and y. And then if you have an initial value problem, then you need to plug in the initial values to solve for the constants. Okay, so that was an example we worked together. Let me work through a couple more examples in the next 10 minutes, and you should stop me when you're confused. So I'm going to work through a couple more examples just to show how it all works out. So the first thing I'm going to do is I'm actually going to work through an inhomogeneous example. So this is going to be a little bit more complicated to solve, but you actually do end up solving it the same way. So the first step is you're going to take x dot and get x double dot is equal to x dot plus y dot plus 9. Note that that's because you're taking the derivative with respect to t of 9t, which is just equal to 9. Okay, so that's just the first step. We just take the derivative. The next step is, well, we're going to replace y dot with 4x plus y plus 3. So that's going to be this step where we're going to substitute that in. X double dot is equal to x dot plus 4x plus y plus 3. Well, the plus 3 we can add in with the 9, so this is just plus 12. So the first step was take d dt of x dot. And the second step here is substitute in y dot. And then the next step, what we're going to do is we're going to substitute in y. Well, we need to figure out what y is, right? So if we take this equation, you get y is equal to x dot minus x minus 9t. And so we can plug that in. And so then you get x double dot is equal to x dot plus 4x plus x dot minus x minus 9t plus 12. And so this is substitute in y. And let's rearrange this. So if you rearrange this, you'll note that x double dot is equal to 2x dot plus 3x minus 9t plus 12. And we can rewrite this as x double dot minus 2x dot minus 3x is equal to minus 9t plus 12. And so this was just rewriting. And we can continue. So now we have a inhomogeneous linear ODE with constant coefficients. And we know how to solve this as well, right? So if we continue this example, the first thing we do is we solve the homogeneous part. So we have lambda squared minus 2 lambda minus 3 is equal to 0. That means lambda minus 3 lambda plus 1 is equal to 0. Lambda is equal to minus 1 or 3. So x homogeneous is equal to c1 e to the minus t plus c2 e to the 3t. Okay, so that's the homogeneous part. But since this is an inhomogeneous equation, you need to have a guess. So an ansatz for your particular solution. And I'm going to guess that xp is going to be at plus b, since I want it to look like the right-hand side. And so we need to take the derivatives. Xp dot is just a. Xp double dot is equal to 0. And so we can plug those things back in to here. So when we plug that in, what we get is we get 0 minus 2a minus 3 times at plus b is equal to minus 9t plus 12. We rewrite this slightly. You get minus 3at plus minus 2a plus minus 2a minus 3b is equal to minus 9t plus 12. Can you explain the ansatz again? Yes, so this is what we spent a lot of time working on Wednesday, which is how do we guess a particular solution? Well, the answer to that is you want the guess to look like your right-hand side of the inhomogeneous equation. And the right-hand side here has some is minus 9t plus 12, and so one reasonable guess is that it's going to be some constant times t plus some other constant. So remember, the ansatz should look like the right-hand side and its derivatives, with some constant coefficients. So you should go back to Wednesday's video if you're still confused by that. Okay, so now we've done that, we can simplify, and the thing we'll do is we'll take this and set that equal to lat, and we'll take this and set that equal to lat, since we're setting equal all the parts with t and all the parts without t. And so we're left with minus 3a is equal to minus 9, which implies that a is equal to 3, and minus 2a minus 3b is equal to 12. And when you solve for that, you get b is equal to minus 6, which implies that our particular solution is 3t minus 6 for the inhomogeneous equation. And now, of course, once we have that, we can plug that all back in. And so our x general solution is going to be c1 e to the minus t plus c2 e to the 3t plus 3t minus 6. Okay, so this gives us a solution to the x in general for this inhomogeneous equation. And of course, we had to use this ansatz to use the method of undetermined coefficients. Now, the next step is, well, now we need to solve for y. So remember that we had, these were our original equations, and this was our solution to x. And so this gave us that y is equal to x dot minus x minus 9t. And we just need to solve for that now. So, well, we know x dot here is equal to minus c1 e to the minus t plus 3c2 e to the 3t plus 3. And so therefore, when you plug that in, y is equal to x dot, which is minus c1 e to the minus t, plus 3c2 e to the 3t, plus 3, minus the quantity for just what x was. Let's c1 e to the minus t, plus c2 e to the 3t, plus 3t, minus 6, minus 9t. Wait, was that minus 9t? Y is equal, yes, minus 9t. And when we simplify this, this gives you y is equal to minus 2c1 e to the minus t plus 2c2 e to the 3t minus 12t plus 9. And so this gives you solutions for both x and y for this inhomogeneous problem. And the main difference here is because it's inhomogeneous, you had to add together a homogeneous solution and a particular solution, which you got by guessing using this ansatz. Okay, and so let me go ahead and give you the setup for this problem, though I don't think I'm going to have time to solve it. So how can you apply this in real life? Well, suppose that you have a model of the human liver. So you want to measure how well the liver functions. And one experiment that people do to measure how well a human liver functions is you inject some TCGSA into the bloodstream, and you measure how much TCGSA is in the blood or the liver as a function of time. And so this is actually, if what we're saying is that in this particular model, we're assuming that the material goes from the bloodstream to the liver at a rate of 6%, and from the liver to the bloodstream at a rate of 3%, and our initial amount was 3 milligrams in the blood and 0 milligrams in the liver. And so this lets us actually create a two-compartment model where we have two different variables. So B is the amount of the serum albumin in the bloodstream, and L is the amount in the liver. And you have a two-compartment model where this is 0.06B, and this is 0.03L. And B of 0 is equal to 3 milligrams, and L of 0 is equal to 0 milligrams. And when we do that, we can write a two-compartment model, and in this sort of two-compartment model, you end up getting a homogeneous system of first-order linear differential equations. B dot is equal to minus 0.06B plus 0.03L. And L dot is equal to 0.06B minus 0.03L. And I am actually going to end here. We'll go ahead and get started with this next Wednesday. But basically, once we've rewritten this word problem in this form, you can apply all the techniques that we've been going through today in class to solve this and figure out how much TCGSA is in the blood or the liver as a function of time. And with that, I will end today's lecture. I will see you on Wednesday.